Okay, let's get started. You guys having fun?
Yeah.
Yeah. Before we start, let's do a little bit of a survey. How many people spent less than 3 hours last week? Okay, less than 6? Or even you guys who have some experience? Less than 6 hours? Or less than 10 hours? Okay, good. Less than 15? Okay, more than 20? It's around 20? Okay.
It took me like 6 hours.
Yeah. It was actually the last one or?
The last one was
Okay. Okay. So my personal position here at Georgia Tech as academics, I really encourage you to study and spend time on my course. But at the same time, you have to consider other courses as well. My job is to force you to sit and spend some time actually learning about this subject. Okay? But at the same time, again, consider other courses and requirements as well. Because we got so much complaint about the amount of the workload that we provide to the student. Also, you don't have to aim like 100%. Like so 7 is the bar that you really have to aim to get A out of this class. And take advantage of the online discussion sections and web stations and come visit us. And we are doing our best to help in any way, right? Lec03 is out, and unlike last 2 weeks, the deadline for Lec03 is actually 2 weeks. In other words, very difficult challenges. Manage your time again for these challenges, but it's the first time you actually do exploitation. This is the main subject of this course. Unlike previously, we learned about tools and require background about the instruction set and whatnot. But we're now going to talk about how to exploit them. So, does anyone know what do we mean by exploitation? We often call exploit or control flow hijacking attack. What does it mean exactly? Anyone? In this course, we consider also proof of exploitations as a way to get the flag. So if you provide flag to me, I know you exploit the program or exploit the challenge that we provide, right? Then what does it exactly mean? Like when we say exploitation, it basically means that there's no particular features in the target challenge that actually print out the flag for you. In fact, this is not the developer's intended behavior of the program. But in your case, you manipulate somehow by leveraging all this property of the architectures and whatnot and property of the bug and change their execution flow. Like in this case, control flow, or you can simply say instruction pointer, in a way that you achieve as an attacker. Particularly in the context of this class, we manipulate the control flow in a way that we can get the flag out of this program. In our server, each program is running on their privileges, right? But we manipulate, right? This is what we mean by exploitation, so that we can ultimately achieve what we want as an attacker. And this happened to be either invoking the shell or getting the flag out of this program. You can think of many different contexts in ransomware, for instance. You exploit the browser, you change the control flow in a way that you encrypt users' data in their target. But in terms of exploitation, it's exactly the same thing. But here again, we consider proof of exploitation as a way to control the instruction pointer and execute and do the behavior that we want or when we expect from this course, getting the flag, right? There are a few hints and guidance that I'd like to share with you. We really encourage you guys to work as a team, but it doesn't necessarily mean that each individual person in team work on individual pieces and share their ideas, right? It's more like given a single challenge, I encourage you to collaborate. But again, the boundary between these collaborations and cheating is very slim. But I think my guidelining principle is that if you did cheat, then you probably know, right? It's more like self-judgment call. But if you think the boundary is kind of slim, then you can ask TA or just write their name as a collaborator. When you're asking questions, you have to be very wise. Otherwise, question can be very vague. Or it ended up spending a lot of time in TA's side as well. Like, hey, how to exploit this one? It's a bad way to ask questions. Like, hey, this is what I assume about these challenges. This is what I did because of this assumption. But it doesn't work. Likely, TA pinpoint, hey, your assumption might be wrong. And the way you check the assumption might be wrong. So that they have more context of helping you guys, right? And in fact, we've been running this class for 10 years. We kind of know what type of expectation, what type of questions that you might ask to us. So we probably know everything about potential questions that you might have. So if you pinpoint the right way, then we're going to help you in the right way as well. So let's discuss a little bit about the past challenges. How is it different this time? No debugging symbols. Why do you think why we didn't provide the debugging symbol at the first place? Making it challenging. In reality, that's how people actually do. Not just to strip the binary, they even obfuscated the control flow. So that it's really hard for any reverse engineers and attackers or end users, like consumers, to understand their logic internally, particularly if you're talking about proprietary software, like Microsoft Word, for instance. Currently, many of the proprietary software provides symbols because of some of the usability issues. Something happened in the end user side. We like to get the crash. We like to collect the crash from your devices and solve them, right? Because of those reasons, they often provide the symbols, I would say, not as part of your binary, but there's a platform that provide these symbols if you want. Microsoft provide their symbol service in public, and even Linux distributor like Ubuntu and Arch, as part of core features of GDB, they provide a remote debugging symbol. Like as part of the building process, they collect all these debugging symbols so that if you want, you can access those informations for debugging. What else have you observed? Anything? Yeah? What we call anti-debugging feature. What else? Yeah. Yeah, that's because we strict the debugging symbol, right?
Oh,
yeah. Any other thing that you observe? What architecture is it targeting? 64-bit architecture. A little bit different than before, but in terms of reading assembly, is not too different. What else? In fact, if you're just using a naive disassembler, we also provide simple obfuscation. It's very naive, but most of the latest IDA or Jydra are smart enough that they can resolve some of them as well for you. But I'm going to describe them in detail later. So in terms of calling convention, again, these are the arbitrary rules that somebody decides. Right? There's no and some architecture use slightly differently. Some of the platform like Windows and Linux and certain versions of the kernel also have a slightly different behavior across their platform. These are just rules, it's a way to pass the number of arguments. But there are a lot of interesting corner cases. What if we provide number of arguments more than the number of register? And can you provide some of the argument bigger than the size of the word? Like I have a structured representations that I want to pass through the argument. And you might remember some C function return some value, which is bigger than your native architecture word, right? like in 64, more than 64 bits, for instance. There should be some convention for those cases, but I think these are mostly ad hoc basis. You can resolve them if necessary. In terms of system call, it's also slightly different. In 32-bit architecture, we use interrupt call. But in x86, 64-bit architecture, we have a specialized instruction called syscall. They're subtly different. The way they handle system call dispatcher routines in the operating system through normal interrupt routine. But system call is very specialized one, so they're very fast. So that the way they handle TLB and cache and all these slightly subtle differences between them. But in terms of writing exploitation, there's just another way to invoke the system call. Again, this is simple convention. These are the obfuscation that we injected. Is there anyone notice what's exactly happening? These are the what we call linear sweeping. Given a for example, if you're using object DOM and GDB, these are typical way they disassemble the sequence of bytes into the instruction. What exactly happening right now? There are two jump instructions, right? Then after that is give group, yeah? Exactly. If you see the content, the jumping target of the first jump instruction, in fact, it's not well aligned. It's right after the jump instructions, right? Why they're doing? Is it a legitimate instruction? Yeah. Yeah, exactly. So particularly in x86, like what we call CISC type of architecture, it's very common behavior. But some of the RISC type of architectures, like say RISC-V and ARM, MIPS, they have a very regularized format of the instruction set. So you kind of don't see those type of behavior. But in x86, jumping between those instructions are legitimate. Sometimes compiler, it's a long time back then, compiler thought this is a way to leverage or optimize the use of the space in the program as well. Or it's actually a pretty good way to optimize your program in terms of cache. But I think in modern standard, this is not a way to save your memory, right? But if you trace these instructions one by one, for example, actually disassemble the B3 instruction pointer there, then you'll see the actual instruction set behind the scene, right? But if you start disassembling the one by one, starting from B0, and this is encoded as a 3 byte, 1, 2, 0, 1, 2 byte jumping instruction, then you will see the next jumping instructions after. But if you disassemble right after the 1 byte, after the second jump, you will see another jump instruction, which you ultimately execute during the runtime. What about the signal? Anything interesting out of the signal? What exactly happening? Other than make you annoyed? Anyone can explain the logic behind the signal handler that we injected to the binary? Anyone attach GDB to here? Yes? Yeah? Yeah? Do you understand how they implement this weird interaction between your program and GDB? Yes? Ignoring the interrupt call. Mm-hmm. Yeah, because of the special instruction called in3, this is a way to indicate the software instruction pointer software interrupt as a breakpoint in GDB. In fact, there's a hardware-based register that you can do But in3 is a common way for debugging, in particular in the software layer. So that if you have these in3 instructions in your program, and GDB thought that this is probably the instruction that GDB itself installed, so that whenever it got the software-based interrupt, then GDB trapped and try to resolve this instruction for you. So one way to bypass this, of course, you can do very careful binary patching, or you can set some of the signal handler by yourself in the GDB so that you can manipulate the behavior, right, accordingly. In other words, enabling GDB itself change the behavior significantly, so that you cannot simply trust the behavior of the program, the arbitrary program under GDB. Even more, you don't have to trust the behavior of the program running inside the virtual machine. So many of the malware and Trojan and virus whatnot, they behave slightly differently across the platform and slightly differently across, I would say, virtual machine environment. Actually. So you have a question? Yes? In this particular case, you can just ignore in3. Either you can but I believe one of the logic that we hear is to actually count the number of signal handlers you invoke. You can manipulate this global variable by yourself. Or you can remove it in a sense that you can binary patching the corresponding instruction with note in a way that you can ignore the number of counter in the signal handler outside of the loop as well. So that, yeah. You can explicitly call if you eliminate the signal handler installations like action, for instance. But I think that's one way. But I think better way to just manipulate the logic that checking this global counter as well as instructions with no. But when you're doing this, you have to make sure this is I'll say expected behavior of the challenges itself, right? Otherwise, it seems like you do something, but which is not something that the original designer expected, then you probably not get the right answer. What about this one? What exactly happening inside? Anyone can describe? Yeah? Mm-hmm. Yeah. So basically, there's a special interpreter on top of our program that accepts some of the user input and behave exactly like the tuning machine, so that they can create or that they can manipulate the memory tape that you provided as initial instruction to this interpreter. And as far as you create the right output, say we're gonna give you the flag. How did you analyze this assembly? Anyone? Yes? Uh-huh. In the GDB, okay, once you eliminate this, probably make the nope on the phase calls, right? And then you work on the final phase. Did you mostly focus on the dynamic behavior of the program, or?
So I
Uh-huh. I see. I see. Once, is there any approach that you guys took? Yes?
It's like, I saw it now, but it showed the example, and then it took me like 5 minutes to figure out, okay, like, I know where to go.
Uh-huh.
So like, I just saw a bunch of dates, and then I was like, okay, I know.
Yeah? Did you take this? Yes?
I just did somewhat the same. I first
Uh-huh. Wow, that's interesting approach. There actually a lot of, I would say, self-contained program can be done in your way. So they lift it to the decompiler output, and it's hard to manipulate assembly, frankly. Right? Just copy this output from the IDA and compile back and just tinker with it. In fact, GDB provide pretty interesting way that you can interact with this dynamic snippet of the code. For example, you can attach the program in the GDB, you can invoke this particular function. And this is something that I'd like to share with you. It works. Let me show you how it works. Can you guys see? Yeah. Let's copy this bomb from the server. And in last week, we talked about how IDA work. In fact, it's exactly the same as Jydra. How many people are using Jydra instead of IDA? Cool. I think both are great too. There's pros and cons, but it's really up to you. But this time, let's try with this Jydra. If you launch the Jydra, this is the ugly Java looking UI. That's the only complaint. But otherwise, in terms of features, it's working pretty well. So you can create the project under here, and then you can import a file, say bomb, which I just copy from the server, and doing the exact same thing. They analyze a binary. You can select which analysis you can perform. It's a time and analysis trade-off, the precision trade-off and time. Just apply, analyze. What does it say? Did they analyze or not? I think they didn't analyze. So the resolution is see, do not use Java. It's so bad. Their UI is so bad. Kill this guy. Just use IDA. It's IDA based on Qt, which is a little bit better than Java. But it's the exact same. So we go to main. You can see the tedious prefix of the main functions, right? In fact, we are interested in the last phase, right? Here. And this is likely the user input. We get the user input to v5, and we're going to invoke this guy. And this guy seems to be an interpreter of this language, right? So one way you can do, assuming that you know the address of these functions, here, right? Let's run the program with the GDB. When you run, it's gonna ask you about the API key, right? But in fact, here we actually don't need anything about those API. You don't have to provide, right? Just run it. Say set the breakpoint on the main. I think you can just start and launch the program and stop, right? At this point, GDB already set up the memory, so you can actually query whatever you want. So one way we can do here, so we know that this function is accepting user input, right? One way we can do is set the break, copy this address, and you can actually say, you can invoke these functions in this way. Say, we need to execute a little bit further to initialize. Go to the main, or we can continue to run. Yeah. See here, it printed out something after we execute, right? This is a pretty good hint. You can keep doing this until you actually match the behavior. One way you can do is set the breakpoint right before, and keep repeating itself until you see the final output of these functions by literally invoking them. So let me try once more and run the program. And we now have a breakpoint at these locations, the beginning of this interpreter. And then you can set the breakpoint right after the print here. Copy. and set the breakpoint in this location. And then you can here we execute these functions inside the GDB, but we set the breakpoint right after the printf so that you can still see how many memory increment happen in this output, so that you can dynamically adjust those values and match whatever comparison routine of the program. So although we highly recommend to work on the static way, but there's still a way to manipulate the behavior in the dynamic fashions so that you don't have to understand the every details written in the GDB. Similar to the Pi challenges in previous BOM lab as well. So Pi routines, you kind of expect the behavior of the program. In fact, you can actually run the program, the instructions inside the BOM and see the result and just compare the final output so that you can save a lot of time of reverse engineering by yourself. Let's talk about the shellcode writing. Is there anyone who can share how you approach the polymorphic shellcode? Yes? Mm-hmm.
I guess what it is pretended to execute more. So it executes it like the backer. So it decrements the AX. And then what you can do is just type in that opcode so you can stop my direct. Then you can check right after for the sign flag. So you set EX to 0. In X 86, it's going to decrement. So then jump.
Yeah, exactly. There's a certain bytecode that changes the behavior in each architecture. In this case, OX40 is increment of EAX in 32-bit architecture, but it considered as a special prefix that manipulate the behavior of the instruction after. So because of those reasons, then you can create a dispatcher routine. So it's the same sequence of bytes behave differently across the architecture, right? Is there anyone who actually discovered this special instruction by themselves? There are zillions of other instructions other than REX. Is there anyone who actually tried? Without looking at this descriptions online? How would you approach if you don't know about REX? Yes? Anyone? Compare by eyes. That's what we exactly did during the competition. Any other people? But unfortunately, this doesn't scale. We have interesting competition in DEF CON in 18. We remember this moment that we analyze. So the challenge here, there's 20 different architectures here. Find one shellcode that works in every single one of them. So how many architecture that you exploited? Do you know the interesting type of king of hill, right? So as far as you maintain this top number of architecture, you will get the point. So basically competition given like on a day of competitions, you have to keep doing this over and over again until you achieve everything. I remember overnight we I would say read through the instruction encoding of 7 different architectures. It's manual online, right? This is a bunch of manual that even I don't know whether this architecture exists even at right now, but we can go through each one of them, find out by eyes, hey, what are the best way to create this special routine? And really, it doesn't work out very well. We ended up doing like 7 or 8, but there's one team that actually did pretty well in automatic way, right? What they actually did is just given a 1 byte or a sequence of byte and increment and try to fudge the behavior of, because they first implement the emulator of each architecture. You can either get it from the online most of the time and manipulate this, I would say, emulator behave in the similar way. And given a sequence of bytes and inject it to every single emulator and see how they behave. And then depending on this behavior, they figured out how to order them in the right way. And then one team actually ended up exploiting 12 different architectures in one day, which is pretty amazing. Yes? Exactly. Yeah. Yeah, exactly. Hey, which one is effectively noped? Which one effectively changed the behavior? You kind of create the map of like approaching with this sequence of byte, right? Keep changing this and see how they behave differently so that they can not only figure out what are the nope operations. The basic idea here is that until you hit the right instruction in your architecture, you need a byte sequence which are simply the nope or equivalent to the nope to you, but there are some meaning in the other architecture. Right here, each emulator job is create a sequence of things that doesn't matter in terms of shellcode, but at the same time, these are the legitimate characters that we can use in this scope that other people can leverage them as a dispatching routine. So you can create this gigantic constraint per architecture in a way that you can combine everything together as a one unified shellcode. But in this particular challenge, we actually provide the nice hint. Yes? Mm-hmm. So most of the instructions are well standardized given the architecture, although we know, say that so for example, some invalid opcode are processed slightly different across the architectures even. Like for example, this ARM implementation of certain Cortex, like or whatnot, and everyone has their own extension even, right? But we have, when you're formulating this, there's a very concrete emulator that we are targeting. Like this is I would say gigantic evaluation routines. So everyone has access to the evaluator, so we can actually query them as well on the game. So that as far as you can exploit the emulator, that's okay, particularly in this competition. So REX is a pretty interesting prefix. In 32-bit architecture, they discard a increment AEX and then rather assign a different meaning of this bytecode. So that if you're using this prefix, when we say prefix of instruction encoding, it basically we are expecting more bytes after. And because of prefix, if you discard the prefix, it's still valid instruction set. But if you're adding the prefix, its behavior becomes slightly different. For example, because of REX bits, you say traditionally add EAX, but because of REX extension, EAX register become different register that is only exists in x86 64-bit architecture, for instance. Or instead of using increment EAX, because of REX bit, it become increment of RAX, for instance. So these are the special prefix to indicate the behavior or encoding of the instruction set followed by this REX prefix. Again, interesting decision they made is to discard this particular instruction that is interesting meaning in the 32-bit architecture, increment EAX, and they become a almost nope-like behavior in 64-bit architecture. So one simple way to achieve this is that you can formulate you can append REX to the nope instructions in x86 64 so that it's still nopes, but in terms of 32-bit architecture is the increment and nope. So that the REX value become different across the architecture. Based on this, you have one unified instruction that jump. You can make a valid jump to a corresponding architecture shellcode, but this particular instruction is shared between these two different architecture. So that as far as you can put increment, EAX, and NOP will be differently interpreted across two different architecture. Right? More concretely though, you can organize the shellcode in this way. First, we like to clear out the EAX. In fact, this interpretation is exactly the same across two different architecture. If you have XOR, EAX, and EAX, there is a byte that work exactly the same across two different architecture. But when it comes to prefix and NOP, they behave differently. And then jump 0 instruction is also shared between these two architecture. So that in terms of 64, they're going to jump because increment EAX is not executed. But when it comes to x86, 32-bit architecture, it becomes 1. So that they can take the corresponding branch to execute the shellcode. What about shellcode mean? How many bytes have you used? Anyone think that is best? Yes?
I got 0.
Okay.
I don't know if it's valid.
Anyone? Other than 0? What was your approach?
I added enough byte the first time.
Yeah. Why does it happen?
The program uses strlen.
Exactly. So how did you come up with this 0 byte? What was your first instruction?
I think it was 0, 0, 0, and so like add each.
Okay. That's effectively, I would say, NOP operation to you, but still contain the 0 byte at the beginning. So any other legitimate way? This is a good way. This is an unintended one. But any other legitimate way to reduce down the number of bytes usage in your program? Yeah.
I wasn't able to gather that. Like using dishes instead of some other ways. It's pretty much spam.
Yeah.
Pushing off.
So previous shellcode is designed to be universal, which means you have to have a lot of boilerplate code that you have to deal with. But in this particular instance, there's a context you can leverage, right? Certain value size of registers are still valid when you're executing EAX. Even proc flag exists in the program, so you can leverage them as well. Another possibility is that you can, in fact, put the shellcode as part of environment variable. In fact, you can leverage those behavior too, right? You injected the shellcode in the environment variable. You manipulate the instruction pointer in a way that you can jump, right? Then effectively you have a very minimal number of shellcode that you can do as well.
This is a question I guess it's related to it's related to like the environment challenge. So
Yeah.
But I noticed like running versus running in normal, there's like differences in address in the stack. Like, also,
Yes.
like what would you say is the recommended way to
So we have a detailed write-up in our tutorial page. You're gonna read today. So if you have that questions, read through our tutorial today. At the end of the tutorial, we have a very detailed guideline how to match these two. And GDB need those environment variables to keep track of how many depth that they're doing and what are the user interface like, how many columns and whatnot, columns and lines and whatnot. And also current program that they're debugging versus current program they're tracing. So all these environment variables encoded as part of a GDB session, but in fact you can easily discard them through exec wrapper. So what we mean by exec wrapper is in GDB, before you execute the program, you have a chance to manipulate the behavior. So the inf, the binutil provided by Linux can be used to set like how many environment variable you want to use, what variable that you want to keep, and what variable you want to drop. Or you can actually clean up entire environment variable as well. Another trick that you're going to use, particularly this week and next week, is a way to tolerate these subtle differences as well. In fact, it really doesn't matter if your shellcode can tolerate these subtle differences between your debugging environment and actual target as well. This is what we call NOP sled. So NOP sled, basically, if you jump in the middle of somewhere, But in fact, it's an obsolete. It's a gigantic prefix of your shellcode that can tolerate this difference between them. This is another common way that you can avoid the subtle differences between your target and what you're debugging. Okay, any other questions? And also, we're going to talk about this obsolete in next week's tutorial as well, so you don't have to worry too much about. Okay, can anyone describe the behavior differences between fget and string length? What exactly fget does? Yes? Why they're doing this? From what you can read from get. I like to get strings. What is exactly C strings? Like C string is something that we create in the language spec, right? Some character that ended by the null byte, which is 0 bytes, right? At the end, to indicate the end of the string. Unfortunately, the actual implementation of get is not like that. They're waiting until user press the enter, like new line character. And this is the moment that fget just stop. Meaning that although they're going to return a valid pointer at the end, and after reading all this one to the buffer that user provide, it might contain 0 byte. On the other hand, string length is very naive. It's going to read until the end of the null byte. So that there are subtle differences between this. A lot of people actually forgot about those subtle differences, so that they make a lot of mistakes when they're using either fget, even scanf has a subtle different behavior as well. So when you're writing your C program, you have to carefully read how they actually behave and implement their specifications described in the man page as well. How many people solve ASCII shellcode? How many people solve? No one? Okay. How did you do? Mm-hmm. Yep. So the general approach that he described just now is what we call self-modifying code. We're going to generate the instruction that doesn't necessarily the ASCII encoded, right? It's kind of an extra payload, similar to what bootloader is doing for the next stage of the executions after you're done with your job. Here we create the multiple stage. There's a one, I'll say, decoding phase that purely written in ASCII character. In fact, if you enumerate all these ASCII characters and disassemble by yourself, there are a bunch of instructions that you can pick, right? And push and pop are well-known instructions that you can leverage in terms of ASCII or alphanumeric characters. One way to create something out of this convention is that if you have particular instruction you want to create on the stack, you manipulate to the simple arithmetic operations, assign certain value to the register, and push back to the stack one by one, right? Then you ultimately have a shellcode on the stack, and later on you can jump to the stack. So that, or you can carefully manipulate the stack pointer in a way that it point to the below of your stack, start constructing your shellcode one by one, so that when you're done, it actually executes your shellcode. Because many of the jump instructions might not be able to contain the corresponding jump target because they are not ASCII character. But there's a lot of interesting ways to solve. But in our side, we have universal, I'll say, encoder. Given arbitrary shellcode, we have a logic that convert this one in the ASCII format. So that given the shell, like any arbitrary shellcode, you can convert it to alphanumeric character. The implication here is that although somebody say, hey, our special string manipulation functions only accept this certain character, so that we are not suffering from this arbitrary shellcode. In fact, this kind of like adult way to filter those out, filtering schemes doesn't work in practice. There's so many ingenious ways to bypass this kind of filtering in reality. You can imagine some IDS type of situation, intrusion detection system, like firewall, right? They keep monitoring their packet and see if any potential shellcode embedded as part of the packet. In fact, you can easily fool those type of systems by encoding your shellcode in the legitimate ASCII characters. So one of the trick here that I described is that say we like to manipulate some of the value in AX, the register, and say this is our goal. Say one payload say I like to create the that as a last bit of the shellcode. So this is how we can encode, right? First, we're gonna zero out the EAX register. So one simple way is you can call XOR. Unfortunately, XOR is not the valid as alphanumeric character. So one simple trick we can do, you can assign a 2 constant to EAX and XOR. And if the 1 bits are cross each other, you ultimately have a 0 value in AX, given an arbitrary value inside the EAX register. So after this to end routine, then EAX might contain just 0 value. And then you can perform some subtraction operation. Because the 2's complement, everything wrap around and ultimately reach the ASCII character that you want to have. And most of the most of the byte range can be covered by the 3 sequence of subtraction operation. So in this case, in order to construct the that, you can start subtracting this 2, 3 value. And at the end, EAX register contain the that, the constant. And when you're done constructing those shellcode, then just push to the stack in a way that you can keep decoding the shellcode from the bottom to the up. And when you're done, it naturally execute the constructed, I would say self-modified shellcode at the end of your stack. Okay? Yes? So if you analyze the behavior of the target that you provide the shellcode to, what they do is it buffer, copy, and start executing, right? If you put your execution code right after, it's below of your shellcode. You're constructing something. You're just writing the extra code at the end of your shellcode. Yeah? Exactly. And then it naturally goes to the next instruction that you modified inside the buffer. Exactly. So in a way that you don't have to jump around. It's naturally construct all the decode all the rest of the shellcode at the end of your buffer, and naturally your transition go to the newly constructed shellcode after. Some of I'll say jump instructions are ASCII too, but the range is very limited, so that you might not have the corresponding range and constant that you want. I believe jump 0 and others are ASCII range. I think if you check one of the reference that we provide, there's a bunch of decoded like table that describe, hey, these are the ASCII characters they can use, and some of them contains a jumping instruction. Unfortunately, they only accept very certain limited range of jumping target. Okay, we now have a tool like shellcode and all the nice dynamic and static tools that you analyze the binary. But starting from this week, we're gonna exploit the vulnerability. So when we say exploit, we're gonna change the behavior of the program as we wish, so that on behalf of the user who run the binary, we can manipulate the behavior and get the flag out of them. And one example that we're going to discuss today is the crank me challenges that we saw in last week's tutorial. So again, crank me has a simple buffer overflow. Previously, we didn't change the control flow, but we simply provide the right password. But in this week, we're going to trigger the vulnerability in a way that although we didn't provide a correct password, we like to get the flag out of this binary. Okay. Also, in terms of Stack Overflow, we prepare tons of interesting challenges like Lec04. You can now actually reach the stack return address on the stack, or some of the encryption, very naive encryption scheme. So when you're providing the buffer, you have to do additional operations on their content. Or you can construct a stack upside down. So we have now new architecture or new convention of the program that are not using stack in the right way, but they're using the reverse way. The implication of this, there's a buffer. Think about how to override them. If you have a buffer, start overriding. There's nothing to override in terms of return value. But in fact, how to change their execution behavior if we have a program that using stack in the other way, right? Hopefully you guys have a great fun. But let me quickly describe about what is Stack Overflow and how we can actually exploit and simple program or template that leverage the programming, a way to control your target programs. Stack Overflow exists like almost 30 years ago. This is one of the very first article described that, hey, there's an interesting type of bugs that this person observed. And in fact, it's so prevalent that literally every single program exposed on the internet has this type of vulnerability. In other words, you can actually break to any single machine by leveraging this Stack Overflow at the time. So there's a nice article and still valid in today's world, what we call Frag Magazine. Frag Magazine share their knowledge in this, I'll say, dark art to the community in very formal way. So if you have time, starting from this article, there's a sequence of article about how to exploit stack and how to exploit some of the mitigations on the Stack Overflow as well, which will be the topic in next few weeks in this class as well. So I highly recommend to digest this article. But in fact, for doing the challenges in Outlet, you don't have to read every single one of them. But if you have time, I highly recommend. So let's talk about Crank Me Challenge. So let's go to here. So let me first copy the Crank Me Challenge. Okay, this is a regular Crank Me challenge. Previously, how did you get the flag? Provide the password, right? But in this case, we are not going to provide the valid password. Again, we like to manipulate the behavior, get the flag without providing valid password, right? This is the unintended behavior of the program. In order to do this, we have to understand how they construct the buffer at the first place. So let's invoke either IDA where is the Crank Me challenge? Yes. So this is the routine. If you decompile, it's pretty simple, right? There's a comparison routine with the buffer. And if it matches with this password string, you print out the print key, print out the flag. Otherwise, you say invalid password. Have you recognized any bugs? What? Scanf. What exactly the bug? Mm-hmm. Exactly. Because of this box that accept arbitrary length of the buffer from the user, unfortunately, the actual buffer within the program is limited. So how many characters it can contain? What's the size of a buffer? 16. How many characters you can put? 15. If you ended up putting 16, there's an extra no byte that ended up overriding something. What are you going to override? Exactly. Store EBP. EBP inside the stack. It might see the immediate impact depending on how program behave, but if program is deep enough, the behavior would be completely different if you start overriding EBP. One of the challenges I described, Lec04, for instance, you cannot reach the return address because it's lacking 4 bytes, but you can still override the frame pointer in a way that you can still manipulate the behavior, right? So in here, we're gonna do some very simple experiment. Say, so we're gonna provide 16. What's gonna happen? Nothing happened. It's very lucky, right? It provides 16, but it doesn't happen. So in this case, we're gonna provide a certain pattern. I just put about 24 bytes. Every byte consists of 8 for A, 8 for B, 4 bytes for C, and 4 bytes for D. So that after providing this pattern to the program, we kind of know that how they actually accept what position of the buffer influence what, right? In this case, if you provide this value, it crash. If your program crash under our server, we're gonna provide a very simple log. But if the program crash in your local environment, you can get the core dump. Depending on your system, core dump might be dropped in current directory, most likely. Or in my case, I put all the core in separate directories so that I can debug whenever I want to. Because core is dumped, you can analyze with the corresponding binary. Say, if you launch the core, and this is the core file that I just wrote, and then this is the context around the time the program stops. What exactly happened? Can you see in the register panel? What's the value of EBP? C. What's the value of EIP? D, right? If you change the value inside the EIP, or if you change the value inside this buffer offset of the CCC, in fact, you can completely control the value of this particular register. And why EIP instruction now pointing to DDD? Yeah, because of the scanf, you ended up overriding store return address. Now, what's the moment that the EIP become the store instruction pointer you override? When pop EVP and return, right? When everything is returned, they took the value on top of the stack and changed the instruction pointer so that you will see the instruction pointer stop after having this value, right? In this practice, what we're gonna do, we're gonna set the breakpoint on this particular moment and see what we can do, right? Another interesting experiment you can do, you can run crank me challenge here, right? And run the program until main, and program will stop at the main if you type main in the phone DBG. And this is right before you execute start, right? This is a sequence of nub instructions, and start contain the logic about processing the password from the crack me challenge. Here we're gonna do some of reverse step. In order to enable this reverse step, you can just record you can ask GDB to record this history. For many modern architecture, enable this behavior by default. But if you want, like software emulation of this behavior, then you can just type record, right? Then it enable the recording of a sequence of instructions that you're gonna execute. And then say we're gonna execute this program further, and it's waiting for your input, right? In this case, let's provide what we provide before. Right? And enter, it stopped. It's exactly the same state that we just did, right? At this point, all the instruction traces is recorded so that you can see information like record, given this amount of buffer that we can record, about half of them are used. At this point, you can actually change the context in the reverse way, what we call reverse step I. So if you type this particular command, it rewinds the history, and then you construct the entire register. For instance, we have context of the register here. Say that stack point to this value location. Can you see the stack on the top? Which contain the store return address from the previous frame. In this case, DDDD. It happened to be the value that you override beyond your buffer. And it's about to take the history, right? About to take the value stored in the stack. If you execute further, in the forward manner, it crashes, right? But in fact, you can go all the way up, say reverse, even continue to the end, the beginning point of a history, and start executing forward and backward if you want. It's a pretty easy way to navigate through the history so that you can understand. And you can even set the breakpoint in forward and backward manner, right? We set the breakpoint in the forward manner previously, but in fact, you can set the condition in the backward manner so they reverse engineer further as well. So if you have this feature, you can just move back and forth and understand those contexts pretty well. Yes? That's a great question. You can think about in the software implementation of this, it's called undo debugging. It's literally the product line you can purchase from the undo company. But GDB now implement, say every single step of instruction you pose, record all the side effects you might introduce as part of this instruction. If you have a gigantic database, what's a side effect of instruction, you can actually construct one by one. Right? If there's a move, say XOR, EAX, and EAX, hey, record the EAX value right before executing this. And if you reverse back, you can restore, right? But this is a naive way. So in fact, this is extremely hard to record every single instructions in this way. So hardware now provide a feature called processor tracer. It's a more advanced form of recording those traces in the hardware. And branch target buffer and recording is another way, a much simplified version of tracking those information. If you purchase laptop recently, last 3, 4, 5 years, many of them have these features. So you can actually navigate it through those without causing much performance overhead. But I think our server doesn't have this feature, unfortunately. Okay. Okay, so far we know how to navigate those. And much smaller way that the phone tool provide, which is a tool that you're gonna use for the rest of the semester, is called cyclic. You can create those patterns more intelligent way. For example, say you want to create a 100-line character, and it provides this sequence of character. One nice thing about this, given any arbitrary window offset, you can represent which bytes that you are in. For example, if you observe instruction pointer contain AAA, you say there is a 0-byte offset on this instruction pointer. If you observe, say, AAAB, then say it's the second byte. And given an arbitrary region, then you can kind of know the exact offset of the buffer corresponding to the value that you observe in the crash. Right? In this case, let's provide this one to crank me challenge. And crank me challenge crash. If you launch, if you navigate this core dump, you can see the instruction pointer point to FAAA. And this is a cyclic input, so that you can check by typing cyclic lookup, its argument is -L, and the value that you want to look up, then it say 20 bytes. If you put additional value after 20 bytes, you're gonna have complete control on the instruction pointer, right? Let's try whether we can actually control, right? Here, so we're gonna use this simple command line for the time being. So if you specify this NE after echo, N stands for no new line, E stands for escaped, so that you can provide the escape character as part of the argument, but we are not going to print out the new characters, new line character after echo. Here, you can provide the escape characters, like say, we like to put that bit. Say, this is the value that we want to, override to the instruction pointer. What we're gonna do, in this particular location of DDD, we're gonna override this 4 bytes address that we want to manipulate the instruction pointer. How would you put this character as part of this argument to echo? What? Yeah, no, what exactly the value we have to provide? So what we are doing here is manual encoding of the sequence of byte. But when it comes to this particular architecture, they understand in the little endian way. So that in order to provide this constant, the integer value, the representation of this integer should be reversed. So that we're going to start with the EF, and then BF, BE, and AD, and DE, in order to manipulate instruction pointer to be that bit. See? Run this. Run this, it crash. If you dump the core dump, say that your instruction pointer is that bit. In other words, you have now capability to manipulate any other instruction pointer. Where should we jump? Any idea? To the call for print key. Here? Should we just call printf? No, print key? What about this guy? It's a print key function. What happened when we jump here? Yes? Exactly. Exactly. So if you jump here, most likely you're going to crash, because the program actually look up the pointer that you pass through the stack. And the argument at the moment, if you jump, likely some of the residue inside the stack. If you're lucky, it's not crash, great. But the flag that we are expecting in the server side need a specific argument, right? In order to set this, you can set your argument by yourself on the stack. That's one way, which is very difficult. Another way is leverage existing code snippet inside your program. In this case, we can jump to here in a way that we first push the Lec03 tutorial on top of the argument, and then call print key functions as part of this instruction. right? We first construct the argument and jump so that print key now know the first argument that we are providing is a Lec03 tutorial, right? So in this particular case, we're gonna modify the instruction pointer to jump here. So let's copy. Say this. (1B) A7 4 8. See, because we manipulate the instruction pointer, now program jump to the right locations in the main program, push the argument, and call the print key so that you can get the flag out of this crack me challenge without providing the passcode. This is how you crack the program, more or less same. Like previous one, we analyze the behavior in the static manner, but here we manipulate the behavior of the program through exploitation. So another cool trick that I'd like to share with you today is that you can actually do all these in programmatic way. In fact, you can manipulate those arguments in the command line with the echo for very quick check, but in reality, it's very annoying, right? You likely make a lot of mistakes as you manipulate this shell script. So one simple way we recommend is to create a script in Python. So this is a special tool called pawn. It provides all these nice mechanisms that you can manipulate the child process so they interact and create the shellcode. This is a very fancy tool. We're going to learn about this tool for the next 2 weeks, right? This is a very simple way you can utilize is that in order to create the child process, literally you can invoke the process. Crank me. Now you have a child instance that you just create. In fact, you can interact by say, I like to send a, what is your right password? So this is the password that I'm gonna send. Either you can send with the corresponding new character or you can do send line. What I just typed is I create the child process. I send this payload, in this case, the password. I just make this child process interactive so that I can continue to operate after. If you run this Python code, let's say Python 3, you say, you prepare the child, invoke the child process, run the program, and then you print out the right password. Password, okay. So in fact, they're actually interacting with the child. In this case, you can provide a crash, the cyclic input, say 100, and you can execute the same. Here, say program crash as a result of the cyclic input, right? And one thing you can do, similar to what you did, what was instruction pointer FAAAA, then you can look up those, cyclic find, and if it return corresponding length of the buffer that you have to prefix before the instruction pointer, and then you can append the value. In this case, instead of providing the depth, we're going to encode the integer in 32-bit. In this case, we provide the packing of the 32-bit, and we're going to provide the depth. So in this case, we're going to convert the depth through the P32, is a packing 32-bit integer, into the byte string, so that we can start appending this payload as a result. And we're going to provide this payload to the program. So let's execute. Yeah, program crash as a result, right? You see that beef, right? So the location that we're gonna jump, what was it? Here. Copy. We just modified the program. If you execute, you get the flag as well. So when you formulate this payroll, you can leverage all these nice tools, which we described today for the very naive way. And we have exhaustive use of this tool in next week's tutorial, right? So that is so fancy that you can even interact with SSH shell and remotely as well. Okay, this is all for today. We're gonna be here, and feel free to take a rest. And we're gonna be here to help you to solve the tutorial. We highly recommend to solve the tutorial here, so you can get help from the other people. Okay, thank you so much. Yes.
So you said that you just jump over the ball function itself as a back push. Is that practically incorporated?
Oh, that's a great question. So if you go this printf function, this is how things operate. You open the proc flag. In fact, you can read the proc flag, but you can write some content to the proc flag as well. If you see here, there's a read, but there before read, there should be, where is it right? Oh, it's a put. Do you see the put? Here, before we read the flag, we are actually writing some content inside the flag. It should become part of the flag that we are getting. So in the reasonable path of the program, as a submission side, we know what content was provided, so that we can in fact trace back what type of instruction was executed on the go as well. Keep appending this information to the flag.
So, like, since you're incorporating that, even if the program doesn't crash and it gives me a flag, it crashes.
That's right.
One of the things are you like pulling it and running it? Yes. Yeah.